Hello everyone, welcome to the 6th lecture on deep learning. Today we're going to be studying adversarial models. So today we're going to start by defining adversarial models, starting with the popular generative adversarial networks. We're going to look closely at their theoretical properties and look at the challenges that are involved in actually training them. And then we're going to work our way through the adversarial, well specifically the generative adversarial network literature, to work out how we can actually get to the state of the art of these types of models. After we've kind of covered the state of the art of generative adversarial networks and how to train them stably, we're going to look at various applications which use adversarial training, including using them to do adversarial attacks on deep neural networks. So by the end of today's lecture, you should be familiar with the foundations and the state of the art of these models, and you'll know what to look out for when training them. So you should have a kind of feeling of how to apply them and what sort of their limitations are and the kind of applications you can achieve by using this training strategy. So let's just look at a very kind of simple example. So just looking at the slide, a generative adversarial network, or a GAN, is a non-cooperative zero-sum game where two networks compete against each other. So one of the networks, this generator network, it generates new samples, these fake-looking images, and then we have this secondary network, this discriminator, which tries to work out whether the generated sample was fake or whether it was real. So it just has a single output neuron which says whether it's fake or real. So I'm going to just drop down to my notes and then maybe explain this with just a simple diagram. So if I just do that. Okay, hopefully that's clear. So basically you start by sampling some noise from a prior distribution, normally from a normal distribution. So we say this is Z, sample from some normal distribution. And then we feed this through our generator, which is just a neural network, a bit like the decoder of an autoencoder, which progressively adds spatial dimensions to the noise. And so it becomes like the shape of an image. So this could be something like, if we were to show it could be like a batch of, say, 64 by maybe 128 dimensions of noise by 1, and this might be a batch of 64 by 3 for RGB by, say, 32 by 32. And these are the spatial dimensions, and these are the feature dimensions. And so we've got 128 features here and just 1 by 1 spatial dimensions. So this generator just kind of increases the spatial dimensions and decreases the feature dimensions typically. So at the beginning, just imagine doing this. What's it going to look like? Well, this is just going to look like complete garbage. It's just going to look like random noise because this is noise and there's nothing to tell it to make it look realistic. So we'll call this a fake image, and it just looks like complete random looking noise. And then you have this. What you do is you sample some real images from your data set. So we could say this is like X sample from D. This is a real looking image of like a cat. I won't pretend to draw a very good cat. There we go. And you have this discriminator network here, which is just like the encoder of an autoencoder, or it's just like any kind of classifier network, which takes as input images, and it has a single output neuron, which either outputs, say, a high value or a low value. And what you do is you try to, and it doesn't really matter which way around, you could say the low values are 0, the high values are 1, the real values are 0, the real values are 1, or vice versa. It doesn't particularly matter so long as you're consistent. But what you do is this network here tries to distinguish whether its inputs are noise or whether they're real. And that's quite easy for it to do at the beginning, right? It's quite easy to tell that this is fake and this is real because this just looks like garbage and this looks like a real image. So this can easily detect, one of them is noisy and one of them is real. So you train this guy for a little bit, or this network for a bit, and it gets better and better and better at distinguishing whether the inputs are noisy or real. But then what you do is you freeze that network, and then you train the generator to fool the discriminator. This is the adversarial part. So now the generator gets better and better and better at creating realistic looking data. This starts to look a bit like a cat. And then it makes this one's task a bit harder. And they play this game against each other where this becomes like a kind of judging the counterfeit images being generated, and this judge gets better and better and better as the inputs become better and better and better, and then the generator gets better and better and better at fooling the judge. So they kind of play this game against each other where they reach this equilibrium where the two networks where this starts to produce hyper-realistic looking results. And there's no kind of pixel-wise L2 measure here. It truly learns the measure. So it learns how to distinguish and how to this function basically learns how far away it is from being real and fake. So it gets progressively improves. Right. So if we just look at the equation here, the game is called a minimax, and it's described in this equation. But the first line here basically shows that the discriminator tries to maximize the log likelihood of the data coming from the data distribution. So x coming from the data distribution. So basically, when the discriminator sees some real data, it tries to output a high value. In this case, just to maximize the log likelihood, max d. And then the second line here shows that the discriminator tries to maximize the log of 1 minus d of g of z. So this means that if the data which it thinks has come from the generator, it tries to score it with a low value. It's got this 1 minus here. And meanwhile, the generator tries to minimize this term. So, which means it tries to do the opposite, fooling the discriminator into outputting a high value. So to summarize, GANs play a zero-sum non-cooperative game, and this zero-sum game is called a minimax. And if one player wins, then the other player directly loses. And at convergence, the generated samples are indistinguishable from the real data, and the discriminator should output a half everywhere. And in game theory, the GAN model converges when G and D reach a Nash equilibrium. So the problem with GANs is that they're notoriously difficult to train, and they usually require lots and lots of data, and attempts to use data augmentation on them often fail because the discriminator becomes quite good at realizing what kind of augmentation strategies are used. Although recently there was an approach that applies data augmentation also to the generated images, and that's shown to greatly improve the quality, especially when there's a small amount of data available. So you can see the linked paper to read about that. But basically they have these kind of 4 problems, and the main problem is this one at the bottom, which I'll come on to. But basically they have this issue of non-convergence where it kind of starts to explode after a while, and it becomes very, very unstable, especially if they're not balanced. So if the generator is too powerful or the discriminator is too powerful, then what tends to happen is the loss goes to 0 for one of those 2 networks, so it becomes like overpowered, and the other network just can't get out of some local minima, so the 2 networks don't converge to that nice Nash equilibrium where they're half everywhere. They also have the problem of the diminishing gradient. So as the networks get better and better and better at generating realistic images, eventually it reaches a point where the networks are, well, the real images are sort of indistinguishable from the fake images. So the discriminator has almost no gradient to distinguish between the 2 distributions. So that becomes hard to train because of stability issues. They're difficult to balance. We've touched on that due to the 2 networks need to have equal capacity, even though they're doing kind of different tasks. One's generating data and one's classifying data. And lastly, they have this massive problem of mode collapse, which we'll come on to in a bit more detail. But just now is probably a good time to just look at some code, just to make this concrete. So this is just a simple GAN. It's just you can click the link in the slide. And this is all just a standard setup. So we have some data loader. In this case, we have the MNIST data set. We have a batch size of 64. The image width is 28 by 28, and it's just a grayscale image. So this is just visualizing some of that data. And then we have some generator function here. And this is just a very naive linear layer generator function. It's not very well written. It'd be better to switch this over to convolutions. And this is a discriminator. Again, it's not particularly clever. It's just few linear layers. And the generator starts by this noise vector, so it starts by it's a batch of, and it's got whatever latent size was. What is that? 100. So it's got 100 features effectively in the very first layer. So it'll be like 100 by 1 by 1, and then this linear layer moves that to 128 features, and then it doubles the features, 256 to 512, 512 to 1024. Then at the very end, it takes all of those features and now roughly, and then it just creates an output which is the same size as the image. So it's quite naive. And the discriminator at the same time starts out with the image and it ends up with just a single value, which is our real or fake neuron. And it uses a sigmoid here to make sure that value can't go under 0 or above 1. So we have these two neural networks, G the generator, D the discriminator, and we have to optimize them both sort of independently. So we actually have two optimizers. So we've got, this prints out the number of parameters, and it's quite good to plot this to see how balanced they are. It's not the best way of judging capacity, because it also depends on what functions are in the neural network, but it's quite useful to just see. So we have these two optimizers. Normally we've just been optimizing one objective, but now we're optimizing two adversarial objectives. And then in the actual training loop, let's just go through. We go through for some fixed number of epochs. Usually you'd have a while true loop, and you would just terminate it when it looks good. Then we iterate through some of the data. This just does it 500 steps before we print some statistics. We grab some of the data from our data set, X. This is just a batch of 64 images. This is all unsupervised, so we're not using the target labels in this process. Then we start by generating a fake image using the generator. So this just takes some random noise vector drawn from a normal distribution. That's what the N stands for there. With 100 features, or 100 elements, and then we pass that through our generator, so we get an image out here. So the G is an image, which we later plot down here, and it starts out looking like random noise, and then we tell the discriminator takes the real data, and in this case it says the real data should look like ones, and in this case and then the discriminator says that the fake data should all output zeros. Then we minimize the binary cross entropy between those two, which is our loss term. Then we optimize both of those values for the discriminator, and we backpropagate through that. So that's just training the discriminator. And then when that's all been optimized and stepped, we train our generator. So we start again with just some random noise drawn from a normal distribution, but now the generator tries to fool the discriminator. So this is the adversarial part. Now it tries to make the discriminator output ones. So when the discriminator was trained, it tried to make the fake data look like zeros, but when we're training the generator, we're trying to make the fake data look like ones. And then we backpropagate through the generator and update the parameters of the generator with respect to that loss. And then that just trains adversarially. So you train the discriminator and you train the generator, and then the discriminator and then the generator, and they play this game against each other where they kind of keep improving. And the samples start to look, they start to look more realistic over time. Again, not great looking samples, but they do start to improve. And the reason they're not particularly great is because of some of the issues, and also because the functions in these networks are not very, very appropriate. You can switch to convolutions and so on. So the main issue of generative adversarial networks is mode collapse. So mode collapse is basically where the generator rotates for a small subset of outputs and the discriminator is unable to get out of the trap. So this is the main limitation of GANs. So let's just say we're trying to generate this distribution over here. And this is ideally how it would train. It would capture all of the modes in the generator. But what tends to happen all the time in GANs, and the main weakness of them, is that the generator gets really, really good at generating just some of the data. So maybe it gets really, really good at generating just the 7s or just the 1s. And then the discriminator takes a while to figure out that it's doing that it's just generating 7s and 1s. And by the time the discriminator has figured out that it's just generating a subset of images, the generator's already moved on to a different mode. It's rotated to just generating maybe like the 4s now. And then the discriminator figures out it's generating the 4s, and then the generator starts to generate the 5s. And then maybe it generates the 1s again. And so it never really captures all of the modes, it just generates a subset of the data. And this is what happens if you train it on CIFAR. Just to show this, you can see this weird chicken-like shape is appearing in many points in the latent space. So a lot of the this is just showing like partial mode collapse, where we can just see, even though it looks like there's quite a lot of diverse images here, actually there's just a very small amount of realistic looking images within a random sample at any point in time. So that's the main problem with generative adversarial networks. And there's a few solutions to this problem, or I shouldn't say solutions, I should say there's a few papers that try to address it, but fundamentally no one's really managed to solve this problem properly. So before I get on to like the main approach, I'm just going to explain the idea of Lipschitz continuity. And Lipschitz continuity is quite important in a lot of deep learning papers, but it's especially important with adversarial models. So simply put, a function is Lipschitz if it's bounded by how fast it can change. So if we look at the definition here, you can see that a function is Lipschitz if there exists some real number such that for every pair of nearby points, x and y, technically we would say that these are points on the graph of the function, but then the absolute value of the slope of the line connecting them is not greater than this real number, this k. So if k were large, it would mean that the function has a very sharp peak or a valley somewhere in it, which can be difficult to find when optimizing. And if k is infinity, then the function is not actually Lipschitz. Whereas if k is like a really, really small number, like 1, then that means that the function is really, really smooth absolutely everywhere. So what if we could make lower the Lipschitzness of the discriminator? If we could slow it down, then if we can do that, we could actually expose it to a lot more data. So long as we've bounded it as bounded like the Lipschitz constant of the discriminator, it wouldn't be too powerful, so that the generator would get stuck in the local minima. And actually, if you do that, it makes it behave optimally according to what's called the Wasserstein metric, or from optimal transport theory. And the first paper to do this was actually what's called the Wasserstein GAN. So what they did in the original formulation of the Wasserstein GAN paper was they just really naively clamped all of the gradient weights within the network to just be like within some small positive negative value. So they used like plus or minus 0.001 or something, if I remember, and it just clamped all of the weights of the paper to be in some hypercube. And this kind of lowered the Lipschitz bound, because it meant that if the weights weren't too large or too small, then it couldn't really scale or stretch the data too much. But what tended to happen is when you're optimizing the discriminator, it would just kind of slide between the corners of that hypercube. It wouldn't really have this nice smooth way of optimizing. So then there came another loss people used, which was a second order gradient penalty, where people added another loss term onto that GAN equation, which basically directly penalized the gradient weights from becoming too large, or too positive, or too negative. So it was like an L2 norm on the gradient weights, and they had to optimize that using second order differentiation, which turned out to be quite slow. But it's worth mentioning that what we really want is like as a distance function on the discriminator. We want the discriminator to have this kind of smooth fall off. So this is a sort of perfect one Lipschitz function. So if you take any 2 points on a distance function, this is the distance to this shape here, the Euclidean distance. If you take any 2 points which are nearby, then they're one Lipschitz, so that the rate of change of this function is 1 until you reach the surface. There are a few sort of abnormalities, but it's 1 everywhere where possible. So distance functions are one Lipschitz functions. And this is like an ideal function. If we could make the discriminator have this property where it's got this smooth fall off to the data manifold, I'll explain this a little bit more concretely when we study energy based learning, where we look at manifolds a bit more clearly. But basically we want this smooth fall off to where the data is. You can think of the data as being this boundary here. So there was this remarkable paper that came from Japan by Takeru Miyoto. And the authors found a way to make the discriminator perfectly one Lipschitz for almost no performance increase by something called spectral normalisation. And these are layers which you use to replace batch norm layers in your discriminator. So normally with a discriminator, if it's a convolutional discriminator, you would have like a bunch of convolutions, then your outputs would be one channel for your true or false value. And normally you would have like batch norm layers. And if you're using PyTorch, you just do torch.nn.utils.spectral norm. You can find it in the docs. You just wrap this around your convolutions like this, and you get rid of the batch norm layers. And the spectral norm is a P2 norm known as a Euclidean norm, where the induced matrix norm is called the spectral norm. And the spectral norm, it corresponds to the largest singular value of the matrix, of this matrix A, which basically just determines how much it can stretch a given vector. So it's quite nice because you just, if you just look at how it works, you just basically renormalize them by this spectral norm, and that has the effect of making that particular function have a Lipschitz constants of 1, which basically makes it like a distance function. And if you just plug these all into your, where you actually do stretching, which is in the convolutions in this case, that just makes this whole function one Lipschitz, which is really cool, and it's really, really fast as well. So you just plug that in. And that has the effect of greatly reducing mode collapse, but it doesn't get rid of it altogether. It just makes training the GANs a lot more stable now. You can just swap these in, and you can actually overtrain this discriminator. You could put the whole thing in an outer loop, in an inner loop, where you can just train your discriminator cell 10 times or 5 times, but it's never going to be able to move too fast and cheat too much, and then your generator is going to be working against this smooth energy landscape. So that moves us on to kind of our first more advanced generative adversarial network approaches, where there's lots of applications and variants on GANs. GANs were the original seminal paper, if you like, and then the field opened up. One of the first nice things that people tried to do was try to make a conditional GAN where you can add, what if we have access to label information, can we use these somehow? And the answer is yes, and it's quite simple. If we just take the labels of some data, so we know this is like a cat or a dog or a horse, and we take this label information and code it as a one-hot vector y, we can just put that y information into our discriminator. So the task now becomes to find x conditional on y. And then you also need to feed that label information into the generator, and then the task becomes generating an image conditional on y. And if you just basically plug this into the GAN equation, it basically makes it into a conditional GAN, so it's quite trivial. How you inject the label information into the discriminator is a little bit more difficult because it's images and you've got this extra y information, so some people like to inject it into the sort of middle layers or inject it into the channels, additional channels, or so on. So just having a look at the code for conditional GAN, this is all the same setup code as the original GAN. This is all the same setup, but now we add the number of labels, which is 10 because there's 10 classes in MList, into the inputs of the generator because it's z conditional on y. And then in the discriminator, we also have to add the labels because it's conditional on y as well, x conditional on y. Then this is all the same. We've got these two networks, but when we create our noise, we also put input y into the generator in the discriminator accordingly. And then when we train, you can see that the generated samples are conditional on the classes, and it actually improves the training stability quite a lot. So if you've got access to label if you've got access to label information in GANs, it's generally quite a good idea to use it if you can. You get these slightly better looking class conditional samples. So what if we don't have access to the labels? Is there a way to still train GANs like the conditional variant, but without access to this supervisory signal? And that there is actually papers which allow you to do this. They're a little bit complicated, but I'll give an attempt to explain it simply. Basically, this is called disentangling the latent space. So trying to come up with some prior distribution C, which we can use to create more meaningful samples. And basically, we start with Gaussian noise, but we add this additional noise here sampled from this prior distribution. So typically, if you wanted to try and find the class labels, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we would basically have noise drawn from a categorical distribution here. So you could sample like randomly from one-hot encodings. Or if you wanted to have, so what the authors do is they have like 10 inputs in C from a categorical distribution, then they might have a few more, 2 more neurons drawn from a Gaussian distribution. So we've got like 12 neurons in C and 12 here in C hat. And what they tend to find is when you train this model, you get the categorical distributions correspond to the digit type, maybe in a different permutation, and then the 2 neurons for the Gaussian correspond to sort of rotations and stroke width. You can see this is like thin 8 going all the way up to a thick 8. So we call these the codes, or the code distribution, this prior distribution. And what we do is we have this other network Q that tries to estimate the conditional distribution of the codes given X. And then what we do is we try to maximize the mutual information between the estimate and the input. And if you go deep into information theory, that's a bit beyond this course, but you can read the paper and you'll understand the definition of entropy there within the paper from the previous lecture. But basically the concept is that the information in the latent codes should not be lost in the generation process. And they use a variational approach like in VAEs to maximize that. So again, there's a Colab example of this, where it's quite naively implemented, again, using not very clever functions in the generation discriminator. And then there's this additional Q network, which was in the diagram. And then when we sample noise, we have to, the sampling procedure is a bit more difficult because we have to draw from a categorical distribution and also from our Gaussians. So it's not just sampling from a normal distribution, it's sampling from these other prior distributions for C. And then the training process basically involves putting that all together, and there's a bit more advanced. You have to look at the paper because there's some variational lower bound, like with a VAE, an additional loss. And then the sampling code is a bit more complex because you have to sort of add you've got to sample from those additional distributions and merge them together to put into your generator function. So here's where we sample from some Gaussians and some from our categoricals. And then if you look through the training, it starts to, this is showing some of the classes. If I scroll down a bit, I'll just stop here. But basically this one looks like quite categorical, almost like the digit type. And this one is probably one of the Gaussians, which looks like it could be the stroke thickness or something which looks like it's quite meaningful from a Gaussian distribution. So that's really cool. They're quite advanced. Okay, so yeah, we had to do this kind of variational approach. And speaking of variational autoencoders, if you remember what a variational autoencoder was trying to do, it was trying to make the latent space permissible to be sampled from, and we minimized that variational. Well, we had that variational lower bound in there, which we had to KL divergence to, if you remember from back when we looked at that. But the idea was that we could somehow make the autoencoder latent space permissible for sampling. And you can actually use an adversarial approach to do this as well. So what you can do is you can just have this mini discriminator network here, which tries to work out if Z looks like it's from a normal distribution or whether it looks like some other distribution. And the discriminator, I should say, just tries to output real or fake if it thinks this looks normally distributed or not. And so you can train an autoencoder and add this additional loss and train it adversarially against this little subnetwork here. And what that will do is it will make this Z look normally distributed over time. So you can click the paper if you're interested. Now that's not going to make the outputs look non-blurry for an adversarial autoencoder, because remember there's still that L2 loss between these two. If you wanted to make this look non-blurry, you would need to do other stuff, like have another discriminator or so on. But it's not. Generally those approaches aren't particularly effective. Okay. Sorry, excuse me. So it's probably worth at this point covering skip connections or U-Nek. So U-Nek is a very, very popular type of neural network, and it's worth mentioning this is not an adversarial method, but because so many of the subsequent adversarial methods depend on these U-Nek architectures, I'm going to introduce it here. So U-Nek is basically just an autoencoder, but we add these things called skip connections between the encoder and the decoder. And this is really popular for doing things like segmentation. So if you've got some like cancer cells or some kitten or some vehicles and you want to try and find the binary masks of them, or if you want to extract like where every single cell is, or maybe different labels, whether this is got a car in it or a pedestrian in it, you would use something like this unit shaped architecture. And basically what it does is it takes the output of layers in the encoder and it appends those to inputs from the corresponding layers in the decoder, assuming they're kind of reflected. And normally if you just trained a normal autoencoder to do this, it would be meaningless, it would be garbage, because what would happen is if you wanted to reconstruct X, it would just take the output of the very first layer and use it as the input to the corresponding penultimate layer here, and you would just end up with a perfect identity, and all of these additional layers wouldn't actually need to do anything. But it works well if you have this paired domain translation task where you want to go from one domain, this domain or distribution of real life looking images, to maybe this other domain where you've got segmentations. So here it needs to learn some additional tasks, and it can make use of all of those that signal information to be passed through. So again, here's some code, and it's just standard setup code. This time we're going to use the CIFAR 10 dataset like you've got in your coursework. And in this example, what I'm going to do is I'm going to just take some grayscale images. So I'm just going to make the inputs black and white or grayscale images. And we're going to ask the network to add color information onto those grayscale inputs. So the input of our U-Nek N is going to be a grayscale image, and the output X is going to be a color image, and we're going to have the loss to make the prediction look like color. And as you can see, the network immediately starts to show realistic looking images, just like in the very first step. And then it learns to add the color information. So that's the original grayscale, and just after a tiny amount of training, it's already started to notice that the sky should be blue. And these look like really realistic images. But obviously they're not unique images. It just it doesn't generate new cats, it just learns to add color, or the sky color. So what does the architecture look like? Well, it's just an autoencoder. So we have this block of functionality here where we just do some convolutions, some normalization, and some non-linearity. And then we have a bunch of downward blocks for our encoder. Then we have a bunch of upward blocks for our decoder. But in the decoder, we have some additional features, I suppose, that we're appending to the inputs. We've got this additional features. Then when we have our forward pass, where we do the actual function or logic, we save the intermediate values. So when we do our first downward layer, we save the output, this beginning of this red arrow, and we save it as conv1. And then we do our pooling layer, and then we save the corresponding output of the second layer. That's this red arrow here. And then we save the corresponding output of our third layer. And then when you do the decoder, you concatenate the inputs of those saved intermediate variables to the corresponding outputs of the layer before. So you can concatenate the input of the previous operation with this output from this one here, and so on, until you have your last layer. So that's how you implement the skip connections with this concatenation operation, where you just sort of add the two together. Or you can concatenate the features together, I should say. Yeah, and then when you train that, it just instantly learns to use all of that signal information where it's required, and then it can do the actual laning to do the other domain-specific task. The problem with this is you need the inputs and the target labels to be aligned with each other. So you need a paired data set. You need pairs of grayscale and color images to train them. So if you were trying to translate between horses and zebras, you would need to use U-Nek naively. You would need a data set where every horse is perfectly aligned with a corresponding image of a zebra, which in practice is extremely difficult to find a data set which is set up that way, if not impossible for many applications. And that brings us on to CycleGAN, which doesn't have this limitation. It's a more complex looking architecture at face value with a lot more losses in the actual optimization strategy, the objective function. But it's really quite a sort of elegant paper other than that. And it's got lots of really nice applications in the paper. Things like doing style transfer from satellite images to Google Map looking images and vice versa. You can have inputs which look like computer games and have the outputs look like real life looking images. So maybe in the future we won't be using rendering engines, we'll just be using sort of neural networks to do all the lighting and simulating all of the weather effects to make them look hyper realistic and so on. So how does it work? Well, it's an adversarial model, but with twin discriminators and twin U-Nek architectures. So if we just focus on this part here, we start with horses from one of the distributions, one of the domains, so this zebra data set. So we've got two data sets which aren't aligned. We've got a data set of horses and a data set of zebras. And we start by sampling X from our data set of zebras, and we feed it through this U-Nek architecture, and we have this discriminator here which takes horses as inputs, and it tries to output whether this looks like it's a horse or a zebra, and this tray has a true or false, and we train this adversarially. So this basically, over time, learns to make the output look like it's from the horse distribution. So it will make the images all look like horses. And then what you do is you do vice versa. You train the horses to look like zebras, and then you have another discriminator here which says this image here should look like a zebra. So it learns to add the stripes back onto the horses. And you train this adversarially as like a separate model. But then the really clever part is there's another loss which goes from the output of this whole process all the way to the input, and it's called the cycle consistency loss, and it's really just like an L2 loss or an L1 loss in the paper. And it ensures that the whole network learns this identity, which means it kind of narrows down the space of solutions that it can learn on and cheat, and it can't learn to cheat by these kind of crazy perturbations, and it makes the whole thing quite stable to train. So yeah, that means you can just have two data sets which are non-correlated, unpaired, and you can learn to translate between the domains. And one more really cool application is the idea of super resolution, and GANs are really effective at this, and in particular there's a paper that's a bit like a conditional GAN and CycleGAN which have been mixed together. So in a conditional GAN, you search the latent space in an iterative process that finds points whose downscaled outputs match the low resolution inputs. But the trick is that you normally search, you have to search this high dimensional latent space, and that would result in too many outputs which would look like garbage. And the authors therefore project the outputs during the iterative search process back onto the surface of some hypersphere, which reflects only the space of outputs which are approximately normally distributed. So depending on how you initialize your search, you get different solutions. So it captures the distribution over the outputs, so they all look like real faces. So basically one of these downscaled images corresponds to lots of potential inputs, and then there's this kind of optimization process which walks along the space of solutions to make sure you get good looking outputs. And this paper caused like a row on Twitter because many people started to notice things like when you give a downscale face of Barack Obama, then the high resolution outputs would whiten his skin. And given what you know about the empirical risk minimization problem, perhaps you can think of a few different solutions that you could do to actually prevent that from happening now. And if you want a hint, you can think of solutions at like a data sampling level, but you can also think of many solutions which make clever use of the conditionals, as in conditional GANs, to tackle those kinds of inherent bias issues. And there's a huge amount of research to be done in this area, making these kind of models less susceptible to such biases. And there's kind of an online example you can try. I tried it with my own face, and I think I tend to look, I don't know, a little bit different because of the inherent biases in the dataset and the kind of faces it's been trained to see under expectation. So one further really great example of these is in the field of anomaly detection. So I'm just going to read through this slide. Basically, unsupervised anomaly detectors learn a normal distribution over the observations. So if you're doing training it on just medical data, if you've just got healthy patients, it will just learn some distribution over the healthy patients. And then when they observe something that's not been observed in training, or unhealthy or dangerous, then the models fail to reconstruct. So they detect it as an anomaly. And there's kind of two types of approaches. You've got just sort of standoff anomaly detectors like Anomaly. It's quite a popular paper by actually Toby Reckon's group. And then you've got region-based approaches, and this is a paper I published in this field. And the region-based approaches basically learn a distribution over in-painted or erased regions. So this is called image in-painting. And I can just briefly conceptually explain the idea. But basically there's some U-Nek kind of architecture, but what you do is you erase a part of your inputs, and then you ask the U-Nek architecture to reconstruct just the erased region. And if you train that adversarially just on healthy patient data, then what's going to happen is if you've got like a brain tumor here, when you erase the region and ask the adversarial network to reconstruct it, then the prediction is going to just look healthy at that region. So there's going to be this discrepancy between the prediction and what was actually there before it was erased. And you can use that to basically, in an unsupervised way, detect where that discrepancy is, looking at where the reconstruction error between the original image and the synthesized image is very large when it encounters those unhealthy regions, and therefore those regions could be flagged as anomalies. So that's really cool. It means you can use these kind of approaches to detect anomalies in your data when you give it new data at inference time. And there's another quite interesting area which uses adversarial training, which is from the field of adversarial examples, or doing attacks against deep neural networks. So I'm just going to read the slide here. But basically, adversarial examples are small but intentionally worst case perturbations that fool the model to output incorrect examples with high confidence. So the most popular example of this is the fast gradient sign method, or FGSM, and this basically adds a pixel-wide perturbation of the magnitude in the direction of the gradient. So it calculates this magnitude of the gradient, and it learns to just do a tiny change, so this very, very small change in a single step, and it's quite efficient in computation time, and that small change completely changes the prediction. So if the model says this is a panda with 57.7% confidence, then this is actually the result of that tiny change, and visually we can't see the change, but this makes the network 99.3% confidence that it's a different class. So there's various strategies based on this idea. Instead of doing one gradient step, you can do multiple gradient steps. You can do momentum-based attacks. And so it creates this whole space of fooling the networks and attacking them, making them do drastically wrong things. And you can buy like clothing, which has some strange-looking badge on it, which is purposely designed to attack any convolutional neural network classification system, so it always thinks you're something else. And there are variants on this. You can do like 3 to 5 pixel attacks. So this is an attack where you're only allowed to modify just 3 or 5 pixels in the image, and you can actually completely change the class just by changing a tiny amount of data in the inputs. And there are also really cool attacks like this on the human visual system. So this is an attack on the human visual system. So this has added some noise, and it's changed what we perceive as humans based on the class. So if you look at these two images, do you think that's a cat or a dog? And this has just made a very small change to this image, and it's changed the class for our visual system, and now it looks more like a dog. You can see the whiskers are less pronounced, and the eyes have a slightly different glint to them. It's quite interesting. And similarly, there's this branch of literature which is how do we defend against adversarial attacks. Well, one idea is to simply add the attacks as training data into our training data set, and hopefully it's therefore going to have to learn to defend against them. And another idea involves examining which functions are susceptible to popular types of attack and choosing different functions from our hypothesis class. So from the space of all functions, we try to identify those which are most susceptible, and we then try to just use different functions which are more robust. And this is actually quite a large arms race, you can imagine. If you did security with me last year, you'll basically see that you've got like methods to attack and methods to defend, and they're constantly fighting each other. But it's worth considering the limit of this game. Like where does this arms race end up? And consider like deep fakes. I think we saw some examples early on. Deep fakes use these kind of techniques like adversarial models as a generative model, and the generative models get better and better and better at producing deep fakes. Unfortunately, what happens? Well, you've got to think, where does this converge? If the deep fake technology is getting better and better and better and better, and the defenses get better and better and better, where does that game converge? And unfortunately, in this case, it converges with the deepfakes being indistinguishable from. They basically have the same pixel values as the underlying real data, as there are only a finite number of pixels in an image, and this distribution can be fully captured as you reach if you think of that limit of that sort of meta adversarial game, you do reach this point in time where the models are producing completely indistinguishable things which cannot be defended against. So in most cases, we actually lose this adversarial game. So it's worth considering. There are still some wins to be had at the moment along the journey, but it's not like where a lot of people are investing their research in these kind of defenses. So there's still immediate wins to be had, but the convergence does look like we'll get to a point where the data distributions become almost indistinguishable. So yeah, that kind of concludes this lecture. There are quite a lot of references we've gone through and a lot of techniques, but hopefully this has given you quite a lot of tools now to go ahead and do a lot of the more advanced deep neural network things, and the really exciting things you often see about on YouTube, those very impressive style transfer applications where you see paintings come to life, you see the Mona Lisa start talking, you see all these very impressive visual looking results, and this lecture should now give you a quite a comprehensive broad view of how all of those techniques fit in by going through these main applications that we've seen today. So this is a rapidly advancing field, but we're starting to see a bit of a plateau in the adversarial literature, especially that issue of mode collapse. By definition, you have this generator which plays against this discriminator, which then goes back into the generator, and you have this cycle, which means that by definition you sort of start to rotate through the modes. So how do we avoid the mode collapse problem? Where do we go? Well, to do that we have to start looking at the energy-based models and how we can see GANs actually fit into this broader picture of learning with the perspective or lens of energy-based learning. So that'll be coming up soon. All right, well that's everything. Thanks very much, and I hope you have a good week.